Figure 1 shows a sketch of a curve with equation y equals f of x, where f of x is this. And then we're being asked to find some points on it, or some asymptotes. So we've got the turning point, P, and we've got lines y equals 1. That gives an asymptote. Because as x gets really big, this thing's going to go to 0. And there's also vertical asymptotes, one of which is at x equals 0, because that's when this part of the function is not defined. And the other one is going to be when x is equal to 3, because that is also when the function is not defined. So a equals 3. We're then asked to find the coordinates of P, justifying our answer. So this is a turning point, and it's going to be when the instantaneous gradient is 0. Right, let me write the function down here. Now, one way of dealing with this, I want to differentiate, is I could split it up into partial fractions and then differentiate. But actually, there's no real need. I can differentiate this function. I can use the quotient rule on it. I think that's probably the easiest thing to do. So we've got u and v. U prime is actually just going to be 0. And v prime, well, if I write v as x squared, I could use the product rule, but it's better just to expand it, I think. X squared minus 3x, then it's going to be 2x minus 3. And f dash x, I don't remember, remember the quotient rule is u dash v minus u v dash all over v squared. So I'm going to get 4 times 2x minus 3. And then this term I would just, so that's a u dash. This term would just be 0, because u dash is 0, all over x squared, x minus 3 squared. And this is equal to 0 for stationary points. And for this to equal 0, it must be that the numerator is equal to 0, which means that 2x minus 3 is equal to 0, which means that x is equal to 3 over 2. Yeah, just note there's no issue in timesing through by this, because I can't have x is equal to 0 or 3, but it's not. I mean, technically, I just need to check for that. Now we're asked for p, so we now just need the y value. So it's going to become 3 over 2 times 3 over 2 minus 3, which is just going to be minus 3 over 2. So it's 4 over minus 9 over 4. And that is the same as timesing by minus 4 over 9. So it's 9 over 9 minus 16 over 9, which gives minus 7 over 9. And therefore, P is going to be 3 over 2 minus 7 over 9. I don't need to, there's only one stationary point, so I don't need to prove that it is a minimum or anything. I've shown why the derivative is 0, and I've got my answer, so I feel like I've done enough justification. We're left to do part C, to sketch this curve involving a modulus. Right, now I've got the original curve. Remember, this is actually 3, and then this minimum is 3 over 2 minus 7 over 9. Okay, going to take this in stages. First of all, I'm just going to draw this without the modulus. And it's going to be a translation by minus 3/2 in the x direction, which means my asymptote to x equals 3 is going to go to x is equal to 3/2. My other asymptote to x equals 0 is going to go to minus 3/2. Y equals 1 is going to stay in the same place. So it's going to look a little bit like that. And my minimum is going to go to 0 minus 7/9. Now, when I then find the modulus of that, the positive part just stays exactly the same, but the negative part is going to reflect in the x-axis and become positive essentially. And the minus 7/9 is going to become positive 7/9. So it's going to go below this y equals 1. Something a bit like that. Maybe I could just exaggerate it a little bit more. Okay, so I've actually done all of this now. We just need to think about what happens when we subtract 1. So I'm going to set up my axes again. Now, when I subtract 1, there's not, the x asymptotes are going to stay where they are. But the y equals 1 asymptote is going to translate by minus 1 in the y direction. And we got this curve looking like this so far. Then now I'm going to take the red curve and I'm going to translate that by minus 1. So instead of it being 0, 7/9, it's going to be 0 minus 2/9. So I've done the coordinate of the turning point. I've done the equations of any asymptotes. What I'm left with is to find the intersections with the x-axis. And this is going to be, I need to solve the modulus of f of x plus 3/2 minus 1 is equal to 0. Now we could turn that into a complicated modulus equation we have to solve, but actually we already know what f of x plus 3/2 looks like. It's this blue curve here. and it's clearly going to be in this region. So it's going to be this. Yeah, it's going to be this part of the curve. So this part of the curve is negative, and therefore it's when find when f of x plus 3 over 2 is equal to minus 1, because it's not equal to 1 in this region. So it's got to be when it's equal to minus 1, because then when I take the modulus, it goes up here, and when I minus 1 from it, that's when I get my 0. So I don't need to turn this into a complicated modulus equation, is what I'm saying. We can just simply look at this. And so it's going to be when 1, I'm just now using my function up here, 1 plus 4 over x plus 3 over 2. And now I add 3 over 2 to this one, so it's going to be x minus 3 over 2 is equal to minus 1. Which means that this is going to equal minus 2. And I can actually divide through by 2 now, just make this back to minus 1, and then make this 2. Multiply through by the denominator. Actually multiply through by minus 1 as well. So x plus 3 over 2 times x minus 3 over 2 is going to equal minus 2. Expand this out, so x squared, I'm going to get a minus 3 over 2x and a plus 3 over 2x, so I can just ignore that. Minus 9 over 4 is equal to minus 8 over 4. So x squared is a quarter. And that means x is going to be plus or minus the square root of that, which is just a half. And we're sorted. This here is going to be minus a half, 0. And I've run that space. But over here, I've got a half, 0. All right, really solid sketch. Enjoyed that. Well done.